Okay, so today we're going to cover section 5, and we're going to learn about the properties of trapezoids and kites. Now, these specific types of quadrilaterals are not parallelograms. All of the quadrilaterals we've learned so far, the rectangle, the rhombus, the square, are all parallelograms. However, these are not. So the first one we're going to talk about is a trapezoid. And a trapezoid is a quadrilateral with exactly one pair of parallel sides. So notice the word here, exactly, because if it had two pairs, then it would be a parallelogram. So it can only have one pair of parallel sides. Each of the parallel sides is called a base. The non-parallel sides are called the legs. Base angles of a trapezoid are two consecutive angles whose common side is a base. So as you can see in the picture, the bases have the parallel line indicators. They have these arrows. So these would be the base of the trapezoid. Now, sometimes when you're given pictures of trapezoids, it may not be sitting on its base. So, for example, I could give you a picture of a trapezoid, and it could be sitting like this, and then it would have the parallel indicators here. This is still the base because it's got the parallel line indicators. These would be the legs right here and here. So remember, the parallel sides are the bases, the non-parallel sides are the legs. And then we have base angles, where the common side that they share is that base. These would be base angles over here and over here. It's got them both in the top and the bottom. Remember, all angles of a quadrilateral always add to be 360. So even though it's a trapezoid, it's still a quadrilateral. Now we're going to see a specific type of trapezoid. This is an isosceles trapezoid. Now I know we talked about isosceles triangles. Now it's an isosceles trapezoid. So if the legs of a trapezoid are congruent, then the trapezoid is isosceles. So notice the legs are indicated with congruency marks, making this an isosceles trapezoid.
Is that only...
Now again, remember, for a trapezoid, there can only be exactly one pair of parallel sides. Those legs cannot be parallel. If they were, then it would be a parallelogram. Trapezoid. So now we have some theorems here, and they're all talking about our trapezoids, an isosceles trapezoid. The first one says, if a trapezoid is isosceles, then each pair of the base angles are congruent. So here, we're going to see that base angles A and D are congruent, and B and C. And the way that we can say that is we've got the congruency marks on the legs indicating that this is an isosceles trapezoid. Theorem 815 is the converse of 814. They flip the if and the then. So now it's saying if a trapezoid has a pair of congruent base angles, then it's an isosceles trapezoid. This might be a theorem you would use in a proof if they ask you to prove, is the trapezoid isosceles? All right, so 816 says that a trapezoid is isosceles if and only if its diagonals are congruent. So remember, this is that biconditional. So we could either read this either way. We could also say if a trapezoid's diagonals are congruent, then the trapezoid is isosceles. We could flip the order here because of the if and only if. Next, we're going to talk about the midsegment of a trapezoid. We already covered when we were talking about triangles before Christmas break about a midsegment of a triangle. Now we can talk about a midsegment of a trapezoid. And it's the segment whose endpoints are the midpoints of the legs. So notice here, it's hitting the two legs. This is a leg, and this is a leg, and it's hitting the leg at its midpoint. Notice the congruency marks here telling us that that is the midpoint. Because remember, the midpoint is going to split that segment into two congruent pieces. Now that midsegment doesn't make those two legs congruent, just it splits it into two congruent pieces. So theorem for the length, or for theorem for midsegment, the midsegment of a trapezoid is parallel to each base, and its length is 1/2 the sum of the lengths of the bases. So what we could also maybe represent this as is the top could be base number 1, the bottom could be base number 2. So to find the length of that midsegment, we could either do 1/2 base 1 plus base 2, or just do base 1 plus base 2 divide by 2. Either way, that's what they're saying right here. They're just using the names of the segments to say that this is base 1 and this is base 2. So for example, if I told you that this was 10 and this was 6, you would take 10 plus 6, divide by 2, 16 divide by 2, and the midsegment would be 8. Let's see. Next, we're going to talk about kites. It's another type of lateral. So a kite is a quadrilateral with exactly 2 pairs of congruent consecutive sides. Now, it's not the opposite sides that are congruent, but it's the consecutive sides that are congruent. So notice here in my figure, it's this side and this side. These are the 2 consecutive congruent. And then over here. Now, if all sides were congruent, this wouldn't be a kite, this would be a rhombus. So all sides can't be congruent in order and also be a kite. So this is consecutive sides that are congruent. Okay, so the first property states that if a quadrilateral is a kite, then its diagonals are perpendicular. The second property, if a quadrilateral is a kite, then exactly 1 pair of opposite angles are congruent. And that's going to be that angle that where the 2 sides that are different meet. So this one and this one are the congruent angles. It wouldn't be A and C. And that's what they put here. So only 1 pair of opposite angles. If both pairs of opposite angles were congruent, then again, it would be a parallelogram. Now that we've learned what all of these figures, the definitions of them and the properties, now we're going to apply all this information in the next examples. All right, so example 1 wants us to find the measure of angle A. Now, here's the scenario where I was talking about where they've placed the trapezoid on its leg. It's not sitting on its base. Remember, the base is where the parallel sides are. So if I were to straighten this up and put it up this way, and then again, you've got your parallel indicators. We've got our congruency marks here. And then up at the top, we could have C, D, A, B. And if C is 100, and because this is an isosceles trapezoid, I know that this angle, this base angle, is congruent to this base angle. So there's a couple different ways we could go about figuring out what the measure of angle A is. So if these are base angles that are congruent, I could do 2 things. I know that the sum of the angles in a quadrilateral are 360, so I could subtract the 2 that I have and get 160. That's going to leave how much I have left for A and B, divide it by 2, and each angle down here would be 80. Now, another way I could go about doing this is, remember, these lines right here are parallel. And I could say, well, if this one's 100, then this is my transversal. A and D are consecutive angles and they're supplements. So if D's 100, A would be 80. So this is another way that you could go about figuring out that the measure of angle A is 80 degrees. All right, example 2. This time they want us to find the measure of angle F. This time they're sitting the trapezoid on its base. Again, notice the congruency marks on the legs, indicating that this is an isosceles trapezoid. So again, I know my base angles are congruent. So now to find the measure of angle F, I could either use the fact that these are consecutive angles and they're supplements, or I could add 49 plus 49, subtract from 360 and divide by 2. I'm going to use the fact that E and F are supplements, so I'm just going to subtract 180 minus 49, and I can get 131. So this angle is 131, and so is angle G. The other way would be to add 49 and 49, get 98, subtract that from 360, and I get 262, divide it by 2, and get 131. Either way, there's usually more than one way to do these. Okay, again, still an isosceles trapezoid. One of the properties we just learned were the diagonals of an isosceles trapezoid are congruent. That's the information I'm going to use to complete this example. So my diagonals are congruent. So it's telling me that KB is 21.9. So this little piece right here, 21.9. MF, the whole thing, is 32.7. It wants me to find this little piece of the blue line. Now, recall that this one here, the KJ, so this diagonal,
Pardon the interruption, Michael Repis, please.
so remember, KJ and MF are congruent. So if I already know the whole thing is 32.7, all I have to do is subtract out the 21.9, and that'll give me that little piece. So I'll go ahead and do the subtraction here. And I get 10.8. Here's example 4. So in kite ABCD, it's telling us the measure of DAB. So right here, this whole angle here is 54. And they're also telling me that CDF, this little one right here, is 52 degrees. Now, if you recall, by definition, a kite is got two pairs of consecutive congruent angle sides. So I could add congruency marks here. Now, I can solve this problem to find the measure of BCD, which is this angle over here. No, I'm sorry, it's the big one up at the top. BCD is up here. So it wants me to find this angle right here. So I can do this two ways. I can either treat this top part as an isosceles triangle. Notice I have congruent sides here. So if I redraw this, recall that base angles in isosceles triangle are congruent. So if this one here is 52, so is this one over here on this side. So this would also be 52. So to find the angle that they want me to find, the tippy top here, I could add 52 plus 52 and get 104, and then subtract that from 180 and find out my missing angle is 76 degrees. Another way I could have solved this, if I didn't realize I had an isosceles triangle, is another property of a kite is the diagonals are perpendicular. So the other way I could do this is pull this little triangle out of here, and it's a right triangle, and this was 52. So what I could do is find the top part. I could add 90 plus 52, and then subtract from 180 and get 38 for this side, and then the other side is also 38. So 38 plus 38 gives me the same answer I got of 76. So a lot of these, there's more than one way to figure out the missing pieces. Again, we're going to pull in our prior knowledge of triangles to solve some of these missing pieces of the quadrilaterals. The last example, example 5, is actually something you would probably see on the PSAT or an SAT. Now, this question, in order to really answer it, we would need our calculators, because when we go to do this, we're going to get our answers in radical form. So you would really probably see this on a standardized test, maybe not so much on our test. If it were on our test, we would ask you to leave it in simplest radical form. So here it says Lucy is framing a kite. So she's making her kite, and she's going to frame it with wooden dowels. And wooden dowels are like wooden sticks that you're going to make the frame of the kite with. She's using 2 dowels that measure 18 centimeters. So we have a dowel here that's 18 and a dowel here that's 18. Then she says 1 dowel measures 30 centimeters, which is going to be up here, it's showing the length of it. So that's this crossbar. Now remember, the diagonals have been bisected, so each side is going to be 15. And then it says, and 2 dowels that measure 27. So these are the 2 congruent consecutive sides. To complete the dowel, she needs a dowel to place along KL. So we need to figure out this piece right here. It says she has a dowel that's 36 centimeters. About how much wood will she have left after cutting the last dowel? So she's got 36 centimeters of dowel for this, but she's not going to need all of it. Now, again, remember, one of the properties of a kite are these diagonals are perpendicular. Notice we have formed a bunch of 4 right triangles here. So what I'm going to do to find the length of this piece of KL, I'm going to do Pythagorean theorem first. I could call this, let's call this x. So this piece could be x. So I'm going to do x squared plus 15 squared equals 18 squared. X squared plus 225 equals 324. Subtract 225. And I get x squared equals 99. I need to square root both sides. 99 I could break into 9 and 11. So I would get 3 root 11. So this is 3 root 11. Again, it wants me to know how long, so I would actually square root 99. And when I square root 99, I get 9.9. So I'll approximate this to about 9.9. Now, I need to find the whole KL. Now, again, notice I've made 4 right triangles, so now I could do the same thing over here. So I could do 15 squared plus, and I could call this y squared equals 27 squared. So square 15, and I get 225 plus y squared. 27 squared is 729. Subtract the 225, and I get 504. Square root both sides, so y is equal to the square root of 504. Now, if it said to leave it in simplest radical form, I could do like a factor tree. 4 times 126, 2 and 2, 2 and 63, 2, 2, 2, and then 9 and 7. And then break down the 9, 3 times 3, 2, 2, 2. Make your pairs. So 1, 2 comes out, 1, 3 comes out. Leave the 2 and the 7 underneath. So this will simplify to 6 radical 14. Again, if I needed to approximate this as a decimal, the square root of 504 is about 22.4. So now I'm going to add those two pieces, because remember I just calculated how long this piece is, this y, and this x. So I need to know how much of the 36 I'm going to use to make KL. So if I add 9.9 and the 22.4, 22.4 plus 9.9, and I get 32.3. Subtract that from 36, and I get 3.7. So about 4 centimeters would be left over. A little bit less than 4. So again, you probably won't see something like this on the test, because most of the time we would ask you to leave your answer in simplest radical form. But you would have something like this on a PSAT or a SAT, where it would probably be in a calculator portion. So that's it for 8.5. In 8.6, we're just going to sum everything up, and then we're going to start reviewing.